Let me, so I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So, all right, so today we're talking about the method of Laplace transforms, and I couldn't go to the rally, so I decided to celebrate MAGA Monday instead, if you're wondering. But a friend of mine went to the rally, and they invited him up front. He and probably his wife and kid, and he was like, and the guy's like, oh, come on, too soon. So he didn't want to be too close to Trump. It's understandable. But so this is the method of Laplace transforms. You have, to start with, a differential equation in y and t with initial conditions. All right. And so so what I want to do to start with here is just give you a motivational example here. So necessarily the things I'm going to show you, we haven't quite worked. I'm just going to have to show you them without, really very good motivation, but here it is. So if we start with d squared y dt squared plus 5 dy dt plus 6y equals 2, well, 1 if t is greater than 1, and 0 if t is less than 1. So this would be a discontinuous forcing function, right? So you take, so here's the starting point. This is a given, and also, well, I haven't stated my initial conditions, but there's initial conditions that are given there too. Oh well. And then I take the Laplace transform of this, and what pops out is the following. You get an s squared big Y minus 2s minus 1 plus 5 times s big Y minus 2. All right, from this I can extrapolate that we're given y of 0 is 2 and y prime of 0 apparently is 1. So we're given an initial value problem, all right? So you take the Laplace transform, and it changes this differential equation in y and t to an algebraic equation in big Y and s. And so that gets us this, all right? Then we solve for big Y. And I'll just kind of shortcut a bit here. You can solve for big Y of s. It's 2s plus 11 divided by s squared plus 5s plus 6 plus 1 over s times s squared plus 5s plus 6 e to the minus s. Uh-oh. Was it something I said? Yeah. Okay. All right. All right. I'll allow it. Let's see here. Probably Democrat. Let's see here. Obligatory. By the way, you're excused from class if you are such. If you need to leave, I understand. I know, there's power in the hat. I've heard. So you do something called partial fractions to get from here to here. And that is a necessary thing for us because once you do the partial fractions, it makes the next step possible. I'm not showing you how to do the partial fractions. Of course, we will be looking at that as the class unfolds here. In fact, today we won't even get close to this, except for I'm just telling you right now. So what I'm doing at the moment is I am giving an example totally out of order before we've developed any of the theory. I just want to show you the big idea to start with, okay? That's what I'm doing right now. I don't usually do this in any class, but I think in this particular stretch, it's really important to have the end goal in mind, because otherwise the whole contraption of Laplace transforms, it's just a bunch of bizarre gibberish. because it doesn't really seem to be motivated from anything in particular. And ultimately its motivation is that it works. I mean, that's the biggest motivation. There are others in terms of like analogies to discrete transforms and things, but if I was to make those analogies, I don't think you guys know those things either. So, but there is an MIT professor who spends about 40 minutes motivating the definition to the Laplace transform as an analog of it's a continuous analog of some sort of discrete Z transform or something. And if you tell engineers at MIT this for about 40 minutes, it apparently makes the Laplace transform understandable. So if you want to, you can look up that video if you know those things. But short of that lecture, I've never seen anybody motivate them. Not really. But I can tell you what they're for. So the point of the Laplace transform is that it allows us to treat discontinuous forcing functions without breaking up into cases. You see this? All right, so like, admittedly, it's dark magic that I'm doing. Let me explain here. So we start with the differential equation in T. We take the Laplace transform. The Laplace transform changes it from a function of time and y to a function of s, which we could identify as frequency, and big Y. So big Y is the transformed variable. Then this next step is just algebra. This is just algebra. You guys, everybody here can do that. All you do is isolate all the big Y terms, factor out something, and divide. That's all that is, right? So just algebra. This is more algebra, but it's the so-called partial fractions decomposition. The point of this is once you do these steps, it then makes taking the inverse Laplace transform an easy business, all right? So our first order of business actually in here is to understand the Laplace transform. First of all, how is it defined, and how do we take the Laplace transform of some basic functions? So that's what we're going to be doing today. But I'd just like to summarize what's going on here. We have an initial, this. How would you have to solve this with previous technology? You'd have to break it up into two cases, right? Break it up into when it's equal to 1, when it's equal to 0. You solve them separately. Then you have to make fit the initial conditions at 0. And then you'd have to continuously extend that initial solution over to the place where it's non-homogeneous, right? It's a pain. You have to break up into cases and meld stuff together. With this, somehow, the Laplace transform weaves, much like Trump, the initial conditions into the algebraic equation for S, right? And you got to be really intelligent to do the weave. So, I'm sorry, referencing stupid recent events. But yeah. So anyway, so our first order of business is to understand L. Once we have that, we already know algebra. Well, then we'll have to learn partial fractions. And that partial fractions, basically the idea is to get back to expressions which we can take the inverse Laplace transform of nicely. So, all right, so let's, without further ado, let's define the Laplace transform. So, definition, let f of t be a function with domain of f equals 0 to infinity, period. The Laplace transform of f is the function big F defined by f of s equal to, this is the definition, integral from 0 to infinity, e to the minus s t, f of t dt. And we also denote this by the Laplace transform of f of s, all right? Sometimes Sometimes we also write the Laplace transform of f of t of s, right? To emphasize the t dependence of the input, where the domain of the big F, the transformed f, is all s in the reals for which the integral exists. All right. So, yeah, let's lead off with a theorem. The Laplace transform of a constant times one function plus another function, right, is what? Integral from 0 to infinity of e to the minus st times c f of t plus g of t dt, right? So I don't usually do this, but I'm going to prove the theorem and state the theorem at the same time. Laplace transforms allow this because pretty much every proof is a straight calculation using improper integration. Like, that's pretty much it. And they're easy because you guys don't care about convergence, and neither will I. So, so you pull out the constant. But this one doesn't really have anything subtle convergence-wise, because the integral of the sum converges if certainly that is going to be the case, that the integral I'm writing down, all the integrals I'm writing down converge if we're given that the integral of f and the integral of g converge. All right, so like what I'm saying is, if f and g are themselves Laplace transformable, then their linear combination is also Laplace transformable. That's a mouthful. So this, of course, is the Laplace transform of f times c at s plus the Laplace transform of g at s. All right. So in short, the Laplace transform is linear. All right, it's linear. So now that we've got that, let's work out a few. So like example 1, what is the Laplace transform of e to the at? What do we got to do? We're up against the integral from 0 to infinity, right, of, how's it go? E to the minus st times e to the at dt. All right? But you guys can do algebra, right? So how do we combine those exponentials? I'll let you add the day. So what we got here, integral from 0 to infinity, e to the minus, well, let's say t times what? Times, well, a minus s, right? That would kind of be the natural thing to write there, right? Can you integrate that with respect to t? I mean, I hope so, right? How's it go? We've got, you know, e to the t times a minus s divided by a minus s, I believe, and that's evaluated from 0 to infinity, right? Now, what do I mean by that, evaluated from 0 to infinity? Let me be careful for a second here, and then I'll go back to disappointing my mathematical friends. So we're talking about the limit as t goes to infinity of, you know, e to the t times a minus s divided by a minus s minus 1 over a minus s, right? That's what's meant by that. We get to take the limit as the upper bound goes to infinity, right? That's what's meant by that. So what happens to this? Let me rewrite, if you guys don't mind. I'm going to erase and rewrite that just a little bit to emphasize. Like, we think about things as a function of s. So writing it in terms of minus s is kind of weird. It's much more natural to write this as minus times s minus a. That kind of emphasizes better the pattern here. So this piece goes to 0 if what? What condition do I need on s? Right idea, but wrong direction. So s greater than a is what we need, right? If s was less than a, then you'd have e to a positive quantity there, right? And that positive quantity would be getting arbitrarily large, which would blow up. So in order for the integral to exist, we need that s is greater than a, but there you go. So there's our first Laplace transform. Woohoo! Laplace transform of e to the at, all right, at s is equal to 1 over s minus a. And that's for s greater than a. So the Laplace transform of the exponential is simply this shifted reciprocal function, right? And let's try to get the most mileage out of this we can. What's the Laplace transform of 1? Let me rewrite that somewhat suspiciously. That's the Laplace transform of e to the 0 times t, is it not? So 1 over s, that's right. You got it. So that's, you know, a little bit weird, but that's, you know, that's what we have. The Laplace transform of 1 at frequency s is equal to 1 over s, and that's for s greater than 0, right? So anytime you Laplace transform a constant, you end up with like that constant divided by s, all right? Example 2. Let's look at the Laplace transform of e to, let's say, the lambda t of s that's going to be 1 over, right, s minus lambda, right? And I'm going to let lambda equals to alpha plus I beta. All right, so I'm going to take the case A, if you like, is alpha plus I beta. If I do that, what happens here? Well, I have, of course, rewrite it out again here. So I've got e to the alpha plus I beta times time, right? That Laplace transforms to 1 over, you know, s minus alpha minus I beta. What should I do? Because we like to keep it real in here, right? I apologize for nothing. What should I do to get that I out of the denominator, right? Multiply by the conjugate. That is the kind of insight that a person who's taking complex analysis should have. Very good. Spread the word. Easy. Hardly a proof to be seen, right? Okay, very good. So yeah, multiply by the complex conjugate. And if we do that, what happens here? Well, we get s minus alpha plus I beta divided by s minus alpha squared plus beta squared. Don't doubt me. If you multiply this out, right? What happens? You got this piece times that piece, right? And this piece times that piece. Notice that the cross multiples, you get a plus I and a minus I of the same terms. So the parts with I cancel out, right? This is by design. And you're just left with the s minus alpha squared, and you've got a, I mean, true enough, it's minus I squared beta squared, but what is that? Well, that's beta squared, right? Because if we square I, we get minus 1, you know? But on the flip side of things, we have over here the Laplace transform of e to the alpha t. Remember, that works out to cosine beta t plus I e to the alpha t sine beta t, right? But we just saw that the Laplace transform is linear, right? And trust me when I tell you that these notions of improper integration extend well into the context of like complex valued functions of a real variable. And as such, I can use linearity to break this up into the sum of the Laplace transform of e to the alpha t cos beta t plus I times the Laplace transform of e to the alpha t sine beta t is equal to s minus alpha divided by s minus alpha squared plus beta squared plus I times beta over s minus alpha squared plus beta squared. All right? Now the reason I wrote it out like this is to make it plainly obvious that we can equate the real part right here with the real part over here, right? And we can equate the imaginary part right here with the imaginary part right here. And as such, we derive that the Laplace transform of e to the alpha t cos beta t as a function of s is actually equal to s minus alpha divided by s minus alpha squared plus beta squared, and the Laplace transform of e to the alpha t sine beta t is equal to beta divided by s minus alpha squared plus beta squared. Right. And these calculations, if you study them more carefully, I believe the terms and conditions in here are that we need s is greater than alpha. S greater than alpha. That pretty much has to be the case because that's what this reduces to if beta is equal to 0, right? And we already know s greater than a is the domain, for the frequency domain for the Laplace transform of the exponential. Hey, special case, what happens when alpha equals to 0? What's like the Laplace transform of just cosine of beta t? What's the Laplace transform of sine beta t? Nobody? I mean, it's just right there. You just have to put alpha equal to 0. What happens? S. Mm-hmm. And the other one? Beta, right? Divided by s squared plus beta squared. Yeah. So these things, you do need to memorize the things I'm deriving today. Because you don't want to you're going to want to know these things without needing to look them up, all right? As you learn the calculational method, it's for your benefit to know these by heart. That said, the way this part of the course works is you do get a sheet of Laplace transforms and their inverses to work off of for the next test. So it's not like a large program of memorization so much here. I'm just telling you as a matter of speed and efficiency, and like you will learn these formulas, all right, if you don't get them already. All right. Let's see how much time I have left. All right. So up next, let us, if I can find a place to erase, I guess we're here. Could we do, what about Cosh and Cinch? How would those go? What if we tried to calculate the Laplace transform, what is this, example 3? Maybe? I don't know, I guess it depends if I numbered things or not. I guess I didn't. What's the Laplace transform of, let's say, Cosh beta t? This would be what? The Laplace transform of what? 1/2 e to the beta t plus e to the minus beta t, right? But we already know the Laplace transform is linear. We can pull the half out, right? And then we've got Laplace transform of e to the beta t plus the Laplace transform of e to the minus beta t, right? And how's that? Well, we get 1 over, what, s minus beta plus 1 over what? S plus beta. I think it's instructive to make a common denominator, right? Like, let's make a common denominator. What do you get here? You get s plus beta plus s minus beta divided by 2 times, well, s plus beta times s minus beta, right? Let's clean that up. There's a 2 that's canceling. The beta cancels. What are we left with? We're left with s divided by s squared minus beta squared. Compare that. Compare that to the formula for cosine. Striking, isn't it? On the basis of the analogy that you maybe just see, what's the Laplace transform of sinh without further calculation? Correct. That is the Laplace transform of sinh. What's the Laplace transform of e to the alpha t Cosh beta t? What do you think? If you had to guess without actually working out all the algebra.
S minus alpha over s minus alpha squared.
You are correct. And likewise, the Laplace transform of e to the alpha t sinh beta t is beta over s minus alpha squared minus beta squared. Did you take this course before? Don't answer that. It's always a dangerous question to ask people. You know, people don't usually like it to that be like, you know, exposed. It's like one of the rudest possible things for another student to do in the midst of class, you know, just saying. I may be referencing another class at the moment. Let the listener understand. Oh, okay, so, great. So one more theorem for today, because actually the things I just circled here are all examples of what's called the shift theorem. So let's look at the shift theorem. It says the Laplace transform of e to the at times f of t of s is equal to something. We're going to fill in that blank, all right? We're going to fill in that blank. How are we going to fill in that blank? Well, we're going to calculate it. Let's do it. So if we're calculating the Laplace transform, this is equal to what? This is equal to the integral from 0 to infinity of e to the minus st, right, times e to the at f of t dt. All right? So that first equality, that's just the definition of the Laplace transform. All right? That's it. Now I use exponential algebra. This is integral from 0 to infinity of e to the minus, and I'm going to do parentheses here, s minus a t f of t dt. All right? Now we're done. See, because this is the Laplace transform of f of t evaluated at s minus a. Or if you like, you could write this f of s minus a if you want me to mix nomenclature. In other words, to calculate the Laplace transform of an exponential times a function that you already know the Laplace transform of, you simply take the known Laplace transform and evaluate at s minus a. I mean, check it out, right? The Laplace transform of e to the, say, alpha t times cos beta t, for instance, right, at s is equal to the Laplace transform of cos beta t evaluated at s minus alpha. Take a equals to alpha, you know, for example. Do you see that? So like if you look at the formula, notice what it is you're taking, and everywhere there is an s, you're plugging in s minus alpha. Do you see that? That's composition. That's evaluation at s minus alpha for s. That's the pattern here. Yeah? So, I mean, I don't usually make people prove theorems in differential equations, but like this is the one place I can reasonably do it, because almost every theorem I'm going to share with you about Laplace transforms is literally a simple calculation, calculus 2 style from the definition. It's like a line or two, all right? So I guess that's it for today. Let me give you your second quiz. This is known as Jack's quiz. What?